Hello once again, AP Calc students. Mr. Record here from Avon High School, and we're taking a look at example 5 from our fictitious topic 8.14, calculating the work. Now again, work is not a topic covered in a traditional AP Calc BC course, as it is not going to be tested on the BC exam, but you're certainly going to see it at the college level. And in certain cases, you might see these problems in a Calc 2 course. And for those of you that are engineering majors, it's very likely that some of these ideas may spring forth in perhaps a physics course that you might take. For the problem that we're going to do today, it's got a little bit of a chemistry twist to it. So we're going to take a look at work and Boyle's law. So if we look at the notes here, and I move my camera over a little bit, whoa, we're going to read the question. It says the pressure of a quantity of gas is inversely proportional to its volume. Now, it's not likely that every single person watching this video has taken some type of chemistry course, but if you have, it's very likely that this formula, pressure equals K divided by volume, is something that you are acquainted with. It was first discovered by a mathematician, Robert Boyle, who was a 17th century mathematician who, as you can see in the little bio there, was an Anglo-Irish natural philosopher, chemist, physicist, and inventor. And he's kind of regarded as really the first modern chemist and one of the pioneers of using the actual scientific method that you may have been taught. So what we're going to do with this formula is maybe rework it a little bit. Just know that if you do a couple of things to it, like maybe cross multiply, you end up with the relationship that pressure times volume is equal to a constant. And it's also likely that you guys may have used this formula in the past where the volume was isolated. And it just means that the volume is inversely proportional to the pressure. Okay? So the best way to kind of think about this is, let's say that you are pumping up a bicycle tire. Most of you have probably experienced that. So you put the manual pump that's got the little sort of, I don't know, pumping mechanism, the handle, right? And you attached the nozzle to your bike air nozzle. And of course, if the bike tire is pretty flat, you can pump and inflate very, very quickly right away. It's because there's really no pressure that's building up. But as you get more volume of air inside of that bicycle tire, you're going to find out that it's a little tougher to pull down on that pumping mechanism. And that is because that there's this inverse proportionality there, right? As we try to enter more air in, the fact that there's more air there means that that pressure is kind of building up. So in our particular problem, it says there's a picture there to the left, and let's say that there's a temperature of a gas that's 300 degrees. Now that's very likely 300 degrees Fahrenheit. Maybe it's our super heated gas at Celsius. I guess it's not Kelvin because we do have the degree symbol there, but don't read a whole lot into that. All right, it doesn't really matter what units we're dealing with. When the pressure of this gas is 1, we know that the volume is 4. And I suppose you can kind of see that from the indicator here. The pressure gauge is 1, and the volume over here is at level 4. Now it says when the pressure is now increased to 2, it's like we have a volume that's now 2. As you can see, pressure here is 2, and the volume of the gas is now 2. What that is saying is very, very clear that the constant of this gas pressure situation is going to be 4, because pressure times volume always has to be a constant. 4 times 1 is 4, 2 times 2 is 4. Okay? Now, if you look at our pictures again, it says in the second picture, it's very clear that our handle was depressed. It was depressed that particular distance, and therefore work has been done. The quantity of gas with the initial volume of 2 cubic feet and a pressure of 400 pounds per square foot, let's say, can expand to a volume of 4 cubic feet. So what I want to do is I want to find the work done by the gas. So I guess what's going on here is that we want this gas to somehow reverse the fact that this lever was depressed and sort of pop it back up so that it looks like the left picture. Okay? And so in order for that to happen, this gas is going to do a little work. We're going to put the gas to work. So for our first part, use the pressure equal constant over V to find the constant. Well, in our problem, we have to recognize what our pressure is, and that pressure is 400 pounds per square foot. Now, we are using these like imperial units. We're not using metric units here, so we need to kind of be comfortable with that. So the pressure is 400, and then that volume for which that pressure is true is going to be at 2 cubic feet. And so we're going to put our 2 here, and you can see very easily that our K value is going to be 800, 400 times 2. That's now a complete Boyle's Law formula for us. So what we have in part B is the fact that we can use the fact that pressure is equal to 800 over the volume, right? Or any other version of that, whichever variables we want to solve for. Let's read B and see what it says. It says, write and evaluate an expression that represents the amount of work to expand the gas from 2 cubic feet to 4 cubic feet. And so we have to really get a handle on what is our independent variable here. It probably seems likely that we want to integrate our Boyle's Law formula. But is it the version that has V as the independent variable or P, pressure? Well, if we start looking at what our situation is, we would read that 2 cubic feet and 4 cubic feet are measures of volume. And so we want the version of Boyle's Law that we found in Part A. So we don't really have to adjust anything, right? We just simply have to throw 800 divided by V in, and we know that we're going to integrate that with respect to V. Okay, now think about this, what we really are doing. We are going to use this constant type of pressure, this 800 over V, over a very short interval of volume change. Maybe we're going to use this from like 3 cubic feet to 3.0001 cubic feet, right? We're going to do just an incremental amount of work. Then what we're going to do is we're going to add up all of those little pieces of work, which is why we integrate, right? And then we can do this integration over our entire span from 2 cubic feet to 4 cubic feet of volume. And that's going to end up being our work. So it's a little bit of a different setup than, say, some of our other examples that quite often used distance as the independent variable. In Boyle's Law, it's very common that we'll use volume, maybe pressure. We could have rearranged it, but in this case, volume is going to be our independent variable. Now, one could go ahead and integrate this without using a calculator. You can get pretty far with it, I suppose, but by the time you start, plugging in the 4 and the 2, things are going to start to get a little bit dicey here, and you might have to resort to a calculator. Now, you could simplify this, though. You could call this 800 times the natural log of 2, right? That would certainly work. But if I wanted to kind of compute a decimal value, maybe I can grab the TI Inspire here just real quickly here. I don't really need to do much of anything sophisticated with this. Just off to the side here, I'm going to type in 800. Where's my 800? There he is, 800 times the natural log of 2, and that's going to spit out 554.518. And so 554.518 is going to be a 3 decimal approximation. The only thing that we're missing here is going to be our units. And our units for work are very traditional, right? Distance and sort of a force. And so we can see that pounds was our force and our distance were feet. So we're once again dealing with foot-pounds. And that is how you could use calculus to solve a Boyle's law problem. Again, a little different because our independent variable was not a distance. All right, got a couple more examples, 6 and 7, I think that we're going to show you. So make sure you stick around for those, as those are very common types of questions that you can encounter in a College Calc 2 course. Anyhow, thanks for sticking around. We'll see you next time.